AP Chemistry, we're continuing with the equilibrium unit, and there are several topics in this, but this is titled Le Chatelier's principle. Okay, so first we're going to start off with the concept of a reaction quotient. So the reaction quotient Q is computed the same way as the equilibrium constant K, except Q is computed using existing, not equilibrium concentrations. So the reaction quotient is used to tell which way a reaction will flow. So if Q is equal to K, the equilibrium constant, then the reaction's at equilibrium and it will stay there. If Q is less than K, what that means is the amount of reactants, the denominator, is too big for the numerator. There's too much reactant and not enough product. So the reaction is going to flow upward. It's going to flow to the right, rather, towards equilibrium. And that means that Q is going to increase until it equals K. So that is said to favor products. It's moving in the direction of products. If Q is greater than K, that means you have too much product for the amount of reactant. So the reaction is going to flow in the reverse direction. It's going to flow to the left, and that is said to favor reactants. So the reaction quotient is computed the same way as the equilibrium constant K, except Q is computed using the existing, not equilibrium concentrations. So the reaction from the previous example in the previous lesson, we had a concentration of H2 and a concentration of I2. So those are the same as we had earlier. You don't have to go back to that example. This is what we came up with for equilibrium concentrations of those two. Now we had a different concentration for the product HI. So this product concentration that you're seeing on the screen now is larger than the previous equilibrium value. So we should expect the reaction to flow from products back to reactants. In other words, if there's too much product for the amount of reactant, then it should flow to the left. And this concentration for HI is bigger than what we got for the equilibrium concentration. So we're going to compute Q the same way we do C. So the law of mass action for this particular reaction is HI squared on top, and then the H2 on the bottom, the 0.65, and the I2, the 1.065. And so now we're going to compute that and see what we get. And we get a Q of 90. So the Q is greater. In the previous example, on the previous lesson, we got an equilibrium constant of 51. But now that we've increased the amount of product, we end up with a larger number than that. So we have too much product for the amount of reactant at equilibrium. So Q is greater than Kc. So Kc was 51 from the previous example. The reaction will move in the reverse direction to reduce the products and create more reactants, and it will continue to move until the reactants have been the product has been decreased, the reactants have been increased, and you get back to the equilibrium constant of 51. Okay, so now we're moving on to a new topic. This is called Le Chatelier's principle. Le Chatelier's principle states that if a chemical system is at equilibrium, is disturbed by a change in either the temperature, pressure, or concentration of one of its components, one of its reactants or products, the system will shift its equilibrium so that it counteracts the effect of the disturbance. In other words, equilibrium is the happy place for that reaction. If you suddenly change something about it, the temperature, pressure, concentration, you throw it out of equilibrium, so it wants to move in the direction to take itself back into equilibrium. So let's see some examples of that. If the reaction changes so that more products are formed, it is said to favor products. If the reaction changes so that more reactants are formed, it is said to favor reactants. So example, the reaction below is initially at equilibrium. If reactants are added or products are removed, the reaction will move toward the products. That's a change in concentration. Could be a change in pressure as well. So if you add either H2 or I2, you don't have to add both, or remove HI, then the reaction is going to flow to the right. Think of the metaphor of a crowded room or a less crowded room. If you suddenly increase the concentrations of H2 or I2, the left side of the reaction, left side of the arrows, become more crowded. So people in a crowded room are going to want to move over to the less crowded room. So the reaction moves to the right. On the other hand, if you left H2 and I2 alone and you removed HI, then that room becomes less crowded. So people on the left side will say it'd be more comfortable if we moved over to the right side, so the reactants move over to the right. So just think of it as crowded or uncrowded rooms. So that would favor products if you either add H2 and I2 or remove HI. If the reactants are removed or the products are added, the reaction will move toward the reactants. It will favor the reactants. So if you remove H2 or I2, the room on the left side of the arrow becomes less crowded, so the HI people want to move to the left, they want to move over to H2 and I2. The reaction moves in that direction. If you add HI, then that room becomes more crowded, the room on the right side of the arrow. So again, the reaction wants to move in the reverse direction. So that would favor reactants if you did either of those two things. Okay. In an endothermic reaction, that means heat is going into the reaction. Heat is treated as a reactant. So heat added pushes the reaction in favor of products. So endothermic means the reaction wants to take in heat in order to make the reaction happen. So if you have H2 and I2 producing 2HI and you put heat into the reaction, into the reactant side, it's going to push the reaction to the right. That type of reaction likes to take in heat in order to move from left to right. So taking in heat, being endothermic, makes it move from the left side to the right side. So that favors products if you add heat to an endothermic reaction. In an endothermic reaction, heat is treated as a reactant. So heat removed pushes the reaction in favor of reactants. So in other words, it needs heat to go from left to right. But if you take the heat away, then it's going to want to move from right to left. You're taking away basically one of its reactants. So it's making the room less crowded on the left side of the arrow, and so that means the reaction is going to move from right to left. That is, it's going to favor reactants. So this is for an endothermic reaction, one that wants to take in heat. In an exothermic reaction, one that gives off heat, heat is treated as a product. So you see how you just kind of added on to the end of the reaction there. So heat removed pushes the reaction in favor of products. In other words, if it builds up heat and you take that heat away, you cool off the reaction, in other words, then it's going to more easily move to the right. It wants to give off heat, and if you take the heat out, you help to just, again, with a fan or something to help the heat get out of that reaction, then the reaction will go more quickly to the right. It'll go from left to right, and that will favor products. So that situation, in an exothermic reaction, removing heat favors the products. It makes it easier for heat to be generated and then removed. In an exothermic reaction, heat is treated as a product. Heat added makes it more difficult for heat to exit and pushes the reaction back in favor of reactants. So in other words, heat is trying to escape. It's trying to get out, but you're shoving heat into it. It doesn't want that. It wants to give off heat. So if you keep shoving heat into it, it's not going to go from left to right as easily, and so it's going to go from right to left. So that is going to favor reactants. Now, pressure increase caused by changing volume for gases only. The reaction below has 1 mole on the reactant side, the N2O4, and 2 moles on the product side, that's the 2NO. So if pressure is increased, the reaction will try to return to equilibrium by reducing the pressure by reducing the number of moles, and that's going to reduce the pressure. This can be done by turning products back into reactants in the reaction above. Okay, so there's you and there's the reaction. And suddenly there's that reaction, it's in its happy place, it's in equilibrium, and suddenly you say, I'm going to increase I'm going to increase the pressure. How could you do that? You could do it by reducing the volume and squeezing the molecules closer together. So that's one way you could do it. So the reaction says to you, I'm not happy. You increased my pressure. I don't want my pressure increased. I was happy. I was at equilibrium. So what's it going to do? What can the reaction do to lower its pressure? What it can do is go from the side that has 2 moles on the right back to the side that has 1 mole. Because according to PV equals nRT, if you increase the number of moles, you increase the pressure. If you decrease the number of moles, you decrease the pressure. So the reaction, the only thing it has control over, it doesn't have control over temperature or volume, it only has control over number of moles. So if you increase the pressure, it's going to say, I want to decrease my pressure by reducing the number of moles, the number of particles I have in the container. So an increase in pressure favors the side, meaning you increase the pressure, it favors the side with fewer moles. It wants to move from right to left. Decreasing the pressure favors the side with more moles. So it's not necessarily left and right, it's which side has more moles. So again, let's say you decrease the pressure. And the reaction says, I'm not happy with this decreased pressure. I want to increase my pressure back to where it was. So how can it do that? It can double the number of moles. It can move from the left side where there's only 1 mole over to the right side where there's 2 moles. Increasing number of moles increases the pressure. So again, the sequence is you decrease the pressure. The reaction says to you, I don't want my pressure decreased. I want to go back up. So the way it does it is by going from the 1 mole side to the 2 mole side. Doubling the number of particles will double the pressure. So if pressure is increased, the reaction will try to return to equilibrium by reducing the number of moles, which will reduce the pressure. This can be done by turning products back into reactants in the reaction above. If the pressure is decreased, the reaction will try to return to equilibrium by increasing the number of moles, which will increase the pressure. This can be done by turning reactants into products 1 mole to 2 moles in the reaction above. So again, this is all according to PV equals nRT. Increasing pressure, increased pressure increases the side with fewer moles. Decrease in pressure increases the side with more moles. That's the way the reaction is going to react. Okay, now we're getting into a special type of equilibrium constant called a solubility product. So we have used the solubility rules that you see there. You have a sheet with that on it for an ionic compound in water. And we have kind of said that a compound is either soluble or insoluble. It's either one or it's the other. So for example, calcium carbonate. If you look down at the bottom right, you see carbonate is in the insoluble column, and it's insoluble with anything except the elements that you see up at the very top there. But calcium is not one of those. So if you have calcium carbonate, which is what eggshells or seashells are made of, then it's not going to dissolve in water. And these solubility rules are always for water. So it's not going to dissolve, but we say it's not 100% insoluble. Little tiny pieces of calcium carbonate can dissolve in water. Nothing is 100% insoluble. So that's what the solubility product deals with. So many of the ionic compounds we classify as insoluble, that is, they don't dissolve, actually do dissolve in small amounts. This means the solution contains some of the dissolved ions, but mostly it remains as undissolved compound. This produces an equilibrium situation with its own equilibrium constant called the solubility product, which has the constant K subscript Sp. Remember, all equilibrium constants have some sort of subscript, and Sp stands for solubility product. So at equilibrium, an insoluble solid is mostly the undissolved compound, but little tiny bits break off and dissolve in the water. So if you start off with silver chloride there on the left, it's going to break into silver 1+ ions and chloride 1- ions, but only a very, very small amount will do that. The law of mass action for that reaction is down below. It's Ksp equals Ag plus times the molarity of Cl minus. Now notice that AgCl is not in the law of mass action there. That's because it's a solid. You do not include pure liquids or pure solids, and AgCl is a solid, so it does not go in that equation. Only the product side, only the right side will go into that equation. Solids are never included in a law of mass action, so only the product side is included. So let's go ahead and write the solubility reaction for the law of mass action for magnesium chloride. So there it is. So MgCl2 breaks into Mg1 plus ions and 2 chloride ions. So the 2 chlorides break into separate ions. So there's a total of 3 ions produced by this reaction. You don't come out with a chloride molecule, a Cl2. That's only with gases does chlorine do that. But in solution, it breaks into an Mg1 plus, a Cl1 minus, and another Cl1 minus that are separate from each other. So you end up with 3 particles in the solution. So the law of mass action for that is Mg2 plus concentration times Cl minus, and you square that because the coefficient in front of Cl is a 2. The coefficients become exponents in the law of mass action. All right, so molar solubility is the number of moles of dissolved ionic compound in 1 liter of saturated solution. So what will happen is the compound will dissolve until the solution becomes saturated. What does that mean? A saturated solution is a solution that has reached the limit of its ability to dissolve any more of a solid. Any additional solid will sink to the bottom. If you take salt, which is NaCl, and put it in water and stir it around, the salt dissolves. But at some point, there's not enough. If you keep putting salt in, you'll run out of water molecules able to dissolve the salt. They'll all have already been used to dissolve earlier salt crystals. So what that means is the remaining salt will not dissolve. It will just sink to the bottom. Once you reach that point where the solid does not dissolve anymore, that's called a saturated solution. So the way we can work these problems is if we start with the solubility product of a compound, we can figure out the concentration of cations and anions, and that will lead us to the molar solubility of the compound. Again, the molar solubility is the number of moles that actually dissolve in the compound. We can also go back in the other direction, and we do both of these things by using a Rice table. So we can go back from molar solubility through number of cations and anions back to the solubility product. We will learn how to convert between solubility product, concentration of ions, and molar solubility. So be sure you know the difference between those two terms, solubility product and molar solubility. We'll talk about it here. Okay, so here's an example. It gives you the solubility product. That's the equilibrium constant for the solubility of lead chloride. And it says that it's 2.4 times 10 to the negative 4. Now it wants to know the molar solubility of 0.2 molar PbCl2. So in other words, how much of that PbCl2 is going to actually dissolve? So there's the equation. So you have 2 chloride ions and 1 lead ion that come out of that. And so we're going to start with 0.2 molar, right? And that's how much you start with. We start with no lead and no chloride ions. They weren't given, so we assume that's 0. Now, we use a variable s, so we're going to subtract s. You could use x like we've done so far, but we just do it to emphasize that it's a solubility equation. So the variable s is used in solubility product problems because it represents the molar solubility. So that's the number of moles that's going to actually dissolve. So that is what molar solubility is. It's the s right there in the change line. Again, if you want to use x, you can use x the way we have. So that means on the bottom, you're going to get 0.2 minus x. Now, for every mole of PbCl2 that dissolves, again, the coefficient in front of PbCl2 is a 1, so it's minus 1s. For Pb2 plus, the coefficient is a 1, so it's plus 1s. Okay, and I'm just writing plus s. X. And then, of course, for the chloride, there's a coefficient of 2 in front of that, so it's going to be, you add those two, 0 plus s is s. Now, for the 2 chloride ions, you have 2s. And so you add those with the 0 and you get 2s. So now we have the algebraic equation for the expressions rather for the equilibrium. Okay, and there's the law of mass action. Again, you do not include PbCl2 in this. So it's going to be the solubility product, the Ksp, 2.4 times 10 to the negative 4 times s for the Pb times 2s squared. So it's 2s squared. So that gives you 4s to the third. Be sure you understand that. You squared the 2s, so it became 4s squared. And then you multiply it by the other s, and it becomes 4s to the third. So now it's just an algebra problem. You divide both sides by 4, and you take the cubed root. And if you're not sure how to do that, ask me. If you're not sure how to do that on the calculator. So you end up with S is 3.9 times 10 to the minus 2 molar. So that's the molar solubility of PbCl2. Okay, now we're going to go in the other direction. The molar solubility of manganese carbonate is 4.2 times 10 to the minus 6 molar. That's how much is going to dissolve. What is the Ksp of a 0.3 molar solution of manganese carbonate? So we're going to start off. There's the equation. Okay, be sure you understand how to write that equation. No coefficients. Or these coefficients of 1. So you start off with 0.3 molar. Start off with no manganese and no carbonate at the beginning, so those are zeros. Then your change line is the molar solubility. It's how much is going to dissolve. And you know that number. You're given that number, 4.2 times 10 to the negative 6th. So now the change line is the amount of reactant that is dissolved. This is the molar solubility. So now we subtract those two right there. Now we go over to the next line. And we know that if we dissolved 4.2 times 10 to the negative 6 molar of MnCO3, since the coefficient of that and the coefficient of Mn2 on the right side of the arrow, Mn2 plus I should say, should be the same. It's a 1-to-1 relationship. 1 mole MnCO3, 1 mole Mn manganese. Okay? And then over for carbonate, same thing. You've got the same number. So first we add 0 plus that number, 4.2 10 to the minus 6. And over here we get the same number. Again, all the coefficients are 1, so all the x values are going to be the same, and you get that. All right? Now, the law of mass action, you ignore what's on the left side of the arrow because it's a solid. So the only two you need to use are the 4.2 times 10 to the negative 6th. And each of those, the carbonate and the manganese, are both have that number, so you're basically squaring that number. And when you square that, 4.2 times 10 to the negative 6th, you get 1.8 times 10 to the negative 11th power. So note that for a very small value of Ksp means it is highly insoluble. Very, very small number. All right, and that takes care of this lesson on reaction quotients, Le Chatelier's principle, and solubility product.